Hey everyone, in today's video I'm going to give you a few things that will help ease you into section 3 of our Infinite Series textbook. Specifically, to start, I'd like to bring up a problem. It says throwback because most years this would be a throwback. I'm actually not sure if we spent time on problems similar to this, but it's definitely something you can do. So let's just take a second here. Our job is to find a function which satisfies these conditions. Basically, it goes through this point, it has this slope, it has this concavity, and the third derivative is always, see how there's no point here? See how there's no point? So the third derivative is always negative 12. And so what we're going to do is we're going to work backwards and say, okay, well, if I know the third derivative is negative 12, I could get to the second derivative by anti-deriving both sides here. Okay, so I get the second derivative, and well, negative 12, that's, and I guess you'd have to say dx, sorry, poor notation. You'd say negative 12x plus c. So we did these like one level at a time, I think. At most, we did like 2 levels, and it was with physics. Maybe you went from acceleration to displacement or something. But, hey, look, we've got this point that helps us out with the concavity function. So we know that the second derivative is 1/5 when x is 0. So 12 times 0, looks like our c is just 1/5. Whoops, and it's second prime, I'm sorry. Equals negative 12x. Whoa. No, everything's fine. Everything's fine. Okay, plus 1/5. And now let's keep going. So I'm going to have you repeat this process until you end up at the original function. Now would be a great time to just pause the video, give it a try, make sure you're good with your power rule, and I'll work on catching up. Okay, so for my first one, I have to use the power rule here. Bring my 2 things up 1 degree, solve for a new c. Okay, now I've got the first derivative. Let's repeat the process one more time. And once again, work with your power rule there. Everything comes up 1 degree. Solve for your new constant of integration. We end up with a polynomial function. A lot of power rule. Wasn't too bad, right? A little tedious. We had to do a fair amount of work to get here, but it worked. Question. Can we make that process more systematic? Let me show you an idea, and the author is going to talk about this in the section, but I just thought it'd be helpful to give you a verbal explanation first. So the standard form of any polynomial, let's say any polynomial centered, whoops, I started putting my words together there. Any polynomial centered at x equals a. And that would just, it's kind of like the vertex, right? If you have a, at some point that's off center, would look like this. You'd have some straight up constant. Then you'd have a linear term with maybe its own constant. Then you'd have a quadratic term if we were still going up. And the quadratic term could have its constant. And this can repeat forever, right? You could have a cubic term. You could have a quartic term. And they'd each would have their own constants. So like this kind of fits our last one. Our first one was centered at 0. So we didn't have to worry about this minus a stuff. But otherwise, I mean, look, we have a constant, we have a linear term, a quadratic term, a cubic term. So this is just a really, really fancy way of kind of writing that out. I also realize it's not in standard form, it's exactly backwards. Normally we would have the biggest coefficient, or sorry, the biggest exponents over here, but I've kind of written it in backwards order. That's okay, let's just roll with it for a second. And what I want to do is derive this down a whole bunch of times. So, okay, first derivative, my constant 0 would disappear. But I would have still my first constant, but my linear term as a whole would disappear because the derivative of x is 1. What do we have over here? Now we'd have to start worrying about some of the other rules. We'd have to use the chain rule on this one because it's squared. So we'd end up with 2 of the original constant, and it would become linear. Deriving this term would bring the 3 down. We'd still have the original constant, and then now it'd be a quadratic term. Okay, 4 comes down, keep the original constant. Now it's a cubic term. And I want to keep going. I want to derive this basically until we have just about nothing left. So second derivative. First constant's gone, but over here, now we would have 2 of whatever the, I'm sorry. This should not be a C1. This should be a C2 because it was on the quadratic term. But otherwise, it was on a linear thing, so that's all we got. The linear piece would disappear in the derivative. Over here, it's still quadratic, so I'd bring the 2 down and I'd multiply it by what else we already had. And now we have a linear term left over. Here, the cubic, so the 3 would come down times the stuff we already had. And let's do 2 more derivatives. Good news, there's fewer things each time. Oops, that's supposed to be next. So let's see. Okay, 2 times a constant. Well, that's still a constant. Derivative of the constant is 0. Over here, we just have 2 times 3 times C3. Again, the linear term's derivative would disappear, leave you with a 1. And over here, okay, it's a quadratic, so now the 2 is going to come down. And then finally, in the last derivative, what we have, we just have this 2 times 3 times 4 times the constant, but the linear term would now disappear. What am I trying to get at here? Why on earth did I just fill your page with this? Well, look at this. The function's value at the center, wherever that is, a, so again, it could be 0, could be 5, doesn't matter, is going to be that 0th constant. That's going to be this one right here. And the function's derivative at that point, well, if again, pretend we're plugging in a everywhere. If we plug in a, well, a minus a, a minus a, a minus a, that's all 0. So the derivative at that point would just be that first constant that we'd have over here. And the second derivative would be, well, it's not. So for the first 2, see how it was just the number that was there? But look at this. Our second derivative was 2 times this constant that's there. And if we were to look for the third derivative, again, at the point A, whatever that is, well, you plug in a over here. This whole term zeroes out. We'd have 2 times 3 times whatever the constant was in the original. And then finally, the fourth, I ran out of room here, I'm sorry. The fourth derivative at the center, yes, that's how you notate the fourth derivative, would be 2 times 3 times 4 as a coefficient. Why do I care? Well, let's flip it around the other way. Okay, maybe I don't have a great way to describe that. How about a simpler way to explain this? I'm never going to get around the fact this first one is just a constant, but let me stick in something. Maybe you're noticing a pattern here. 2 times 3, 2 times 3 times 4. That's part of the factorial pattern. And that's going to be very important for us. So like all these derivatives, I'm going to rewrite them using factorials. C0, C1, second derivative. Hey, that's 2 factorial, because 2 factorial is just 2, C2. The third one there. What? Oh, look, that's 3 times 2. Yeah, okay, times 1 doesn't do anything. So it's really 3 factorial. And then the fourth one looks like 4 factorial, C4. So check this out. The nth derivative of any of the center point of the function is just n factorial times the coefficient you started with here. Or, in other words, if I knew just the derivative, sorry, dang it, I made a mistake, I'm sorry. If I knew just a point on the graph and I knew its derivatives, I knew a couple derivatives over it, couldn't I use that to help me figure out these coefficients? And I could bypass all the integrating we had to do over here. I could bypass all the integrating. I could just say, oh, if I know the second derivative is 5, then the coefficient I need in my polynomial on that quadratic term is just 5 over 2 factorial. Isn't that kind of cool? Let me generalize that for you. I just need like one more step here. So you could either say the nth derivative at the center is n factorial times that coefficient. Or some people prefer to think of it this way. They prefer to think of it as the nth derivative at the center. They just preemptively divide out the factorial equals the nth coefficient. So I could figure out if I'm building a polynomial, as long as I know the derivative, as long as I know a few derivatives in the same place, it's very easy for me to fill this out, which I think is kind of cool. So I've got a practice here. Similar style problem. Oh, and pretend this last one, well, it doesn't matter. We'll just say it's at 24. Here's a new set of information. Can you build a polynomial that matches all of this? So it has to go through the point 2, 4. Its slope at that point has to be -3. Its concavity is 8, et cetera, without anti-deriving it 4 or 5 times. Let's see. I will work through this. You could certainly pause and try and work ahead of me. That would be super fine. Let's see. We're going to use this idea that the nth derivative again equals n factorial times the appropriate coefficient here. So my goal is basically just to fill in this equation I highlighted in yellow way up here, but with something that'll fit all of this. Notice how all the points are given at 2. That tells us the center of our polynomial, where it is built, where it is modeling from, is 2. Okay, so let's see. How about I know the function at 2 is 4, which means 4 equals, and this would be the 0th order, the 0th derivative. So in solving for the original, hey, the original constant, or not the original, the 0th constant is just going to be that first point. Because 4 over 0 factorial, remember 0 factorial is 1. That might be worth writing down somewhere. And now let's repeat with the next one down the line. Okay, so the first derivative is -3. That means that -3 is equal to, and again, it was the first derivative, so my n is going to be 1, and then times the first constant. So I'm going to divide, I'm going to isolate the constant. Our linear constant is just -3. Because again, -3 divided by 1 is 1. It becomes interesting once you get past the first order. So now that we're in the second derivative, what the second derivative is at the center is 8. And that's 2 factorial times the second coefficient. So now you can see why some people prefer to start with it pre-divided out. You go either way, it doesn't matter to me. Let's go ahead and divide it out. That means 8 divided by 2 factorial is going to be our quadratic coefficient, which means that coefficient, in fact, actually, you can leave it either way. Let's just keep in mind it's 8 over 2 factorial, and let's simplify that to 4. And I'm just going to repeat here till we get to the end. So the third derivative is -10. Since it's the third derivative, it's 3 factorial times the third constant, the cubic one. And I'll just divide that out to get my third one. I don't know why I'm rewriting this twice, but I'm kind of stuck in the pattern, so I'm going to go ahead and do it. Let's see, and 3 times 2 is 6, so I guess you could reduce that to 5/3 if you wanted. And finally, 24 is our fourth derivative. So our quartic constant or coefficient, 24 over 4 times 3 times 2 times 1. Could that simplify? Yes. 24 times 24. Okay, 24 equals 1. So our polynomial that fits all of this stuff is, again, I'm just going to follow this pattern we have up here. Be our 0th constant, which we said was 4, plus our linear constant times a linear term. Our center, our a value was 2, so that's why I'm going to do minus 2. It's linear, so it doesn't need a exponent. Let's see, our quadratic coefficient was 4. And then x minus our center, again, following along with the pattern up here, so it was x minus a squared, so a was 2. What else? Then we had 5/3. That was our cubic one. Whoops, sorry, that's a 2. And then our last one was 1, x minus 2, the 4th. I know it's not in standard form, and it's maybe not necessarily simplified. That is okay. Polynomials that look like this are acceptable to us this chapter. Remember, our whole goal is to have some equations that model other more difficult equations. In this chapter, we are going to use this method where, hey, we know a point, we know a couple derivatives. We're going to use that to systematically build the very special polynomials that seem to model these more difficult functions. Additionally, one thing I just want to point out here, you could even go simpler than this. You did not have to simplify the coefficients. So we could have operated with these as well. So we could have had 4 plus or minus 3. The first one was, you could have left it as 8 over 2 factorial, x minus 2. You could have left this one as 10 over 3 factorial, and it doesn't bother me. And it won't bother AP either, 24 over 4 factorial. In fact, there will be times where you might actually want to leave it with the factorials in and not simplify it, because it might help you better. And we might just be looking for patterns later on. So, okay, if you turn the page, you'll just see, as always, our process is we read, we look for things to highlight, and then we summarize. So you'll see all the things that I'm going to have us summarize in class. You might take a second just to read over these, because then you know what's important as you're reading through the chapter. I recognize the chapter, this chapter is going to be dense, guys. There's a lot of math that is being demonstrated for you. There's times where the author is taking a derivative in front of you, so I know that can be kind of dry to read. There's going to be some new notation that can be kind of hard to follow. Just do your best. Again, remember, what's the first thing we do when we come back together? We're going to discuss, we're going to highlight, we're going to take notes and summarize. So let's make a trip through that, and I'll see you guys on Monday.